I want to tell you about the day I realized that everything I thought I understood about time might be backwards. You see, most people think the past determines the future. That's obvious, right? What happened yesterday shapes what happens today, 'cause comes before effect. That's how time works. And for most of my career, I thought that too, even though I'd seen quantum mechanics do some pretty strange things. But then I encountered an experiment, a thought experiment at first, then a real one, that suggested something impossible. It suggested that a choice you make today might reach back and change what a photon did yesterday. The future influencing the past. Now, I'm going to tell you how I wrestled with this idea, why it bothered me so much, and what I finally understood about the nature of reality. Because this isn't just philosophy. This is what quantum mechanics actually tells us about our universe. Let me take you back to when I was first learning quantum electrodynamics, QED, as we call it. This was in the late 1940s. And I was trying to reformulate how light and matter interact. I was young, maybe a little arrogant, and I thought I had a pretty good handle on quantum mechanics. I'd worked on the Manhattan Project. I'd solved some tough problems. I understood that particles could behave like waves, that you couldn't know both position and momentum precisely. All that strange but manageable stuff. But there was always this nagging thing about measurement in quantum mechanics that I couldn't quite swallow. You see, in classical physics, Newton's physics, if you want to know where a particle is, you just look at it. Sure, your measurement might disturb it slightly, but that's a technical problem. The particle has a position, and you're just finding out what it is. Past, present, future, they're all laid out like a film strip. Deterministic, clear. Quantum mechanics said something different. It said that before you measure, the particle doesn't have a definite position. It's in a superposition, existing in multiple states at once. Only when you measure does it collapse into one definite state. Now, I never liked that collapse language. It sounded too magical, too much like consciousness was required. I preferred to think about paths, all the possible paths a particle could take, and how they interfere with each other. That's what led me to my path integral formulation. But even that didn't prepare me for what John Wheeler suggested in the 1970s. I was at Princeton, and John, brilliant guy. Always thinking about the deep conceptual stuff, he described this thought experiment to me. He called it the delayed choice experiment. And when he explained it, I remember feeling that old familiar sensation, that queasy mix of excitement and intellectual discomfort that means you're about to learn something fundamental. Here's what John proposed. Take the famous double slit experiment, where you shoot photons at a barrier with two slits, and they create an interference pattern on a screen behind it, proving they act like waves. But if you measure which slit each photon goes through, the interference pattern disappears, and they act like particles instead. Standard quantum weirdness. I was comfortable with that. But then John added a twist. What if you delay your choice of whether to measure which slit? What if the photon has already passed through the slits? In fact, what if it's almost at the detector, and then you suddenly decide whether to check which path it took? According to quantum mechanics, the result should be the same. If you choose to measure which path, no interference. If you don't measure, interference appears. But here's the disturbing part. The photon passed through the slits before you made your choice. So how does it know whether to behave like a wave or a particle? It seems like your future decision affects the photon's past behavior. John looked at me with that mischievous grin of his and said, "Dick, it's like the photon goes back in time and changes what it did." And I thought, that can't be right. So I went back to my office and started working through the mathematics. Because that's what you do when something bothers you. You calculate. You don't just philosophize. You work out what the equations actually say. I started with my path integral formulation, which I developed in the 1940s. The basic idea is this. A particle doesn't take just one path from point A to point B. Instead, it explores every possible path simultaneously, and you add up contributions from all these paths with phases to get the probability of where it'll end up. Now, this sounds wild, but it's mathematically precise and it works. It gives you all the right answers. It explains interference, diffraction, all of quantum mechanics in a beautiful, unified way. So let's apply this to the delayed choice experiment. Imagine a single photon heading toward our double slit apparatus. In my formulation, the photon doesn't choose to go through the left slit or the right slit. It takes paths through both, and through neither, and through everywhere else, for that matter. All these paths contribute to the amplitude. When the paths through both slits arrive at the same point on the screen, they can interfere constructively or destructively, creating the interference pattern. That's the wave behavior. The photon is exploring both slits simultaneously. But now, let's add a detector at one of the slits, something that will tell us, yes, the photon went through here. What happens in my formulation? Well, the detector becomes entangled with the photon. The paths where the photon goes through the left slit are now correlated with the detector, being in a state that says photon detected here. The paths through the right slit are correlated with the detector staying quiet. And here's the key. When you have which path information, even potentially, the phases of the paths from the two slits no longer maintain their relationship. The interference washes out, not because you disturb the photon mechanically, but because the information exists in the universe somewhere, and that changes which paths can interfere. Okay, so far this is standard quantum mechanics. But now comes Wheeler's twist. What if I delay my choice of whether to turn on that detector? I remember sitting there, pencil in hand, thinking, let's be precise about timing here. Say the photon enters the apparatus at time t1. It would pass through the slits at time t2, and it hits the final screen at time t3. Wheeler's asking, what if I don't decide whether to activate my which path detector until time t2.5 after the photon has passed the slits? My first instinct, trained by years of classical thinking, was that this shouldn't matter. The photon already went through the slits. It either went through one or both, and my later measurement should just reveal what already happened. But the quantum equations didn't care about my instinct. When I worked through the math, the answer was clear. The final result, interference or no interference, depends on what measurement you set up at the end, regardless of when you make that choice. If you measure which path at the end, you get particle behavior. If you don't, you get wave behavior and interference. The mathematics was unambiguous. But I still felt like I was missing something. How could this not be time travel? How could the photon know what I was going to do in the future? I want to tell you about the conversations I had trying to make sense of this, because I think they reveal something important about how physics works and how we fool ourselves. I talked to Murray Gell-Mann about it. Murray, my colleague at Caltech, brilliant guy, Nobel Prize winner like me, though don't tell him I said that, we had a competitive relationship. He listened to my concern and said something like, Dick, you're thinking about it classically. The photon doesn't have a path until you measure. There's no what it did independent of measurement. And I said, yes, Murray, I know that's what the Copenhagen interpretation says, but it still sounds like we're saying the measurement reaches back and determines the past. He shrugged. Murray was pragmatic about these things and said, the math works. Why do you need a picture? But I did need a picture. I always needed a picture. That's how I think. I need to be able to visualize what's really happening, not just push symbols around. So I tried different ways of thinking about it. First approach, maybe it's not that the future affects the past, but that the photon somehow anticipates what measurement will be made. I rejected this immediately. That's nonsense. That gives the photon or the universe some kind of precognition. That's not physics, that's mysticism. Second approach, maybe there's no such thing as the photon went through the left slit or the photon went through the right slit until we measure. Maybe these statements are simply undefined before measurement, like asking what's the marital status of the number 5. It's a category error. This was closer to what Bohr would say. I'd had many arguments with Niels Bohr about quantum mechanics back in the day. Well, not exactly arguments, Because you didn't argue with Bohr, you got swept up in his philosophical tide and came out more confused than when you started. But Bohr's point was that you can't separate the quantum system from the measurement apparatus. They form one whole. You can't ask, what was the photon doing when nobody was looking? Because what it's doing only has meaning in the context of a measurement. I understood this intellectually, but emotionally, I resisted it. It felt like giving up on objective reality. Third approach, maybe all possible outcomes happen, and we just experience one branch. This was Hugh Everett's many worlds interpretation, which was gaining some traction in the 70s. In this view, when the photon reaches the apparatus, the universe splits. In one branch, it goes through the left slit. In another branch, the right slit. And when you measure, you don't collapse anything. You just find out which branch you're in. I found this intellectually interesting but profligate. Do we really need to multiply entire universes every time a particle interacts? It seemed like a lot of ontological baggage for what was essentially just a calculation tool. But here's what struck me as I explored these interpretations. None of them actually involved the future changing the past. They just seemed that way if you insisted on asking classical questions. Let me explain what I mean. In special relativity, Einstein's theory, there's a clear structure to causality. Events inside your past light cone can affect you. Events in your future light cone can be affected by you. Events outside your light cone, in the elsewhere, are causally disconnected. Now, in the delayed choice experiment, your decision about which measurement to make happens at time t2.5. The photon hits the final detector at time t3. These are both in your future light cone when you set up the experiment, so there's no causality violation in the relativistic sense. The weirdness comes from our classical intuition that says the photon passed through the slits at T2, so it must have been something at that point, wave or particle, left or right. But quantum mechanics says no. That's not a valid question. The photon at T2 is in a superposition. It doesn't become a wave or a particle that went left or right until you complete the experiment. I remember the moment this really clicked for me. I was teaching an undergraduate class. I always learned the most when teaching. And a student asked Professor Feynman, "Does the photon know we're going to measure it?" And I started to answer in my usual way, but then I stopped and said no. The photon doesn't know anything. There's no photon traveling through the slits making decisions. There's a quantum amplitude, a mathematical object, that evolves in time. We call it a photon, but that's just shorthand. The actual thing is the amplitude, and it doesn't have a classical trajectory. The student looked confused, so I tried again. "Look," I said, "you're asking a classical question about a quantum system. It's like asking, when did the quantum amplitude decide to be read? It never decides. It never is just one thing until the measurement is complete." Now, here's where things got really interesting for me, because Wheeler's delayed choice wasn't just a thought experiment forever. In the 1980s and 90s, people actually did these experiments. I want to tell you about one that particularly fascinated me. Alain Aspect and his colleagues in France, brilliant experimentalists, they set up a version of the delayed choice experiment using actual photons and fast-switching devices. The idea was to make the choice of whether to measure which path while the photon was in flight. They used something called a Pockels cell, a device that can switch in nanoseconds to decide, after the photon had passed through the apparatus, whether to direct it to a which path detector or an interference detector. When I heard they were doing this, I was excited, because despite all my mathematical understanding, there was still a part of me that wondered, what will nature actually do? The result, exactly what quantum mechanics predicted. If the Pockels cell switched to measure which path, no interference. If it switched to allow interference measurement, there was interference. Every single time, no exceptions. The photon's behavior correlated perfectly with a choice made after it had passed through the slits. But here's what I realized, and this is crucial. The experiments didn't show reverse causation. They showed something more subtle and, in a way, more profound. They showed that reality doesn't have the properties we thought it did. Let me explain what I mean by that. In classical physics, we assume something philosophers call counterfactual definiteness. That's a fancy term, but it means this. If you could have measured something, then that something had a value, whether you measured it or not. For example, I have a coin in my pocket right now. I haven't looked at it, but it's definitely either heads or tails. If I checked, I would have found one or the other. The coin has that property, independent of my observation. Quantum mechanics denies this for quantum systems. The photon passing through the slits doesn't have the property went through left slit, or went through right slit in any definite sense. Not until the entire experiment, including the final measurement, is complete. It's not that the photon is both or is neither in some mystical sense. It's that the question itself doesn't have an answer until you specify the complete measurement context. I used to explain it to my students this way. Asking which slit the photon went through before specifying your final measurement setup is like asking, is Shakespeare's Hamlet fundamentally a play about revenge or about indecision before specifying whether you're analyzing it as a Renaissance revenge tragedy or as a psychological character study? The framework you use to ask the question partially determines what answer is meaningful. Now, that might sound like I'm saying reality is subjective or created by consciousness. I'm not saying that. The measurement apparatus is physical. It's not about minds or consciousness. It's about which physical interactions are allowed to occur, which correlations are established in the universe. But what I am saying is that reality doesn't have all the properties existing simultaneously in some observer, independent way. Properties are contextual. They emerge from interactions. This still bothered me, though, because it seemed to violate something deep about how we do physics. We're supposed to be able to rewind the tape, look at any moment, and say this is what was happening. We're supposed to have an objective account of events. And then I had a conversation that changed my perspective entirely. It was with a younger physicist. I won't name him because he might not want the attention. But he asked me a simple question that I should have asked myself years earlier. He said, "Professor Feynman, when you calculate probabilities in QED using your path integral method, at what point do you consider the photon to have gone through a particular slit?" I thought about it. In my formulation, I sum over all paths. The photon explores every possible route simultaneously. I don't ever say it went through one slit or the other during the calculation. I only get a definite answer at the end when I compare the sum of all amplitudes to the measurement. I don't, I said. I never assign it a definite path until the endpoint. Right, he said. So why are you bothered that the delayed choice experiment doesn't assign a definite path until the endpoint? And just like that, I saw it. I'd been inconsistent. I developed a mathematical formalism that explicitly avoided assigning definite classical properties to particles in flight. That was the whole point of the path integral. But I'd still been holding on to a classical intuition that particles must really be doing something definite at every moment. The delayed choice experiment wasn't showing that the future affects the past. It was showing that my own formalism was correct. Properties only become definite at the end of a complete quantum process, not at intermediate stages. Okay, but let me push this further, because there's a more subtle issue I wrestled with, and I think it's worth sharing. Even if we accept that properties emerge from the complete measurement context, there's still something weird about the delayed choice setup, and it has to do with when things become real. See, in quantum mechanics, we have this thing called the quantum state or wave function. It evolves smoothly and deterministically according to the Schrödinger equation, or in my language, according to the path integral formulation. Everything's fine until you measure, and then you get a definite outcome. But here's the puzzle. When does the quantum state know that a measurement is coming? In the delayed choice experiment, imagine the photon has passed the slits and is traveling toward the detector. At this point, we haven't decided yet whether to measure which path or allow interference. The quantum state is still evolving, still in superposition. Now, at the last possible moment, we flip a switch. We choose our measurement. How does the quantum state adjust to give us the right statistics? I spent a lot of time thinking about this, and I realized I was making another classical mistake. I was imagining the quantum state as a thing out there, traveling through space, that had to somehow hear about our measurement choice and respond. But that's not what the quantum state is. The quantum state is a mathematical tool we use to predict measurement outcomes. It's not a physical field in the same sense that the electromagnetic field is physical. It's a summary of all the information we have about possible measurement results. When we choose our measurement at the last second, we're not sending a signal backwards to the photon. We're specifying which question we're asking nature. And quantum mechanics gives us the probability distribution for answers to that question. Let me give you an analogy I came up with, though all analogies break down, so don't take it too literally. Imagine you're looking at one of those ambiguous images, like the famous duck, rabbit drawing. You know the one. It can look like a duck's head or a rabbit's head, depending on how you look at it. Now, suppose I show you this image, and I wait until you've been looking at it for 5 seconds before I ask, is it a duck or a rabbit? Your answer depends on which question I ask, obviously. But we don't say that my question changed what the image was during those first 5 seconds. The image was always ambiguous. It had the potential to be seen as either, and my question selected which aspect you pay attention to. Quantum mechanics is similar, with the crucial difference that it's not about psychology or subjective perception. It's about which physical correlations get established. The photon in superposition has the potential to display wave, or particle, like behavior. The measurement apparatus selects which potential gets actualized. And this selection doesn't propagate backwards in time. It determines which history becomes real for you, the observer embedded in this branch of the quantum state. But, again, this many worlds language bothered me. I didn't like multiplying realities. So I kept pushing on the question, is there a way to think about this that doesn't require multiple universes, consciousness, or backwards causation? And I realized, maybe we've been thinking about time wrong all along. In classical physics, time is like a river. The past flows into the present, which flows into the future. Cause and effect march forward. We slice space-time into now at different moments, and we can, in principle, say what's happening everywhere now. But in special relativity, there's no universal now. Different observers moving at different speeds slice space-time into now differently. The present is relative. And in quantum mechanics, maybe we need to take this even further. Maybe we can't even ask, what's the state of the quantum system now? Independent of specifying the complete measurement context, past and future. This is where I started to see the connection to something John Wheeler said to me once. He talked about it from bit, the idea that physical reality emerges from information. At the time, I thought it was too philosophical, but now I wondered if he was onto something. What if the delayed choice experiment is telling us that information, specifically which measurement you perform, is more fundamental than we thought? Not in a mystical sense, but in a precise physical sense. The information content of a measurement setup constrains which quantum amplitudes can interfere. In the delayed choice setup, when you choose to measure which path, you create a physical correlation between the photon and the detector. This correlation, this information, prevents interference. It doesn't matter when you establish the correlation, as long as it's established before the final outcome. The photon doesn't know about your future choice, but the quantum amplitude for the whole process, from source to final detector, depends on which physical arrangements are in place, including your last second switch. I remember writing in my notebook, the past is not fixed until the present completes it. And then I crossed it out and wrote, no, there is no the past independent of the measurement context. Stop thinking classically. But, even after all this reasoning, there was still something that nagged at me. And it came back to something very personal. When I was working on the Manhattan Project, building the atomic bomb, I was very aware that my present actions would shape the future in irreversible ways. I felt the weight of causation moving forward. What we did in those laboratories in Los Alamos would kill people in Hiroshima and Nagasaki. Cause and effect. Clear and terrible. So how do I reconcile that lived experience of forward, flowing causation with what quantum mechanics seems to say about measurement and context? And I realize there's no contradiction. Macroscopic events like explosions, like cities destroyed, emerge from countless quantum events all decohering together, creating an effectively classical world. At that scale, the past is fixed. Information has propagated. Correlations are established everywhere. But at the quantum scale, where you can carefully isolate systems and preserve superpositions, the rules are different. You can ask questions that don't have determinate answers yet. You can set up situations where the choice of what to measure matters in surprising ways. The delayed choice experiment works because we're clever enough to keep quantum systems isolated until the last moment. We're asking nature a question at a scale where nature hasn't decided the answer yet, where the answer depends on the question. So here's what I finally understood after years of thinking about this on and off. The delayed choice experiment doesn't show that the future changes the past. It shows something more profound. The past doesn't exist in the complete, determinate form we imagine. Let me say that again because it's important. When we think about the past, we imagine it as a fixed sequence of events, things that happened, definitively in one way and not another. The photon went through the left slit or the right slit. That's the past. We might not know which one, but it definitely did one or the other. Quantum mechanics says no. That's a classical prejudice. The past is better thought of as a collection of quantum amplitudes, potentialities, that only crystallize into definite events when they connect to a measurement in the present. Until that measurement, the past is, in a very real sense, not fully determined. And this isn't mysticism. It's not about consciousness or observation in the everyday sense. It's about physical interaction. When a measurement apparatus interacts with a quantum system, it establishes correlations, entanglement between them. That entanglement is what makes outcomes definite. In the delayed choice experiment, delaying your choice of measurement means delaying which correlations get established. And since those correlations reach back through the entire experimental setup, it seems like you're changing the past. But you're not. You're determining which aspect of the quantum amplitude becomes real. Here's the key insight I had. There's no single, absolute history. There are multiple consistent histories, and which one you ask about depends on how you complete the quantum process. Now, I know this sounds like the many worlds interpretation, but I don't think you need to go that far. You don't need to say all histories are equally real in different universes. You just need to say that until you complete a measurement, the question which history occurred doesn't have a unique answer. It's not that the photon did multiple things. It's that what the photon did is not a well-defined concept until you specify the measurement. Let me give you another way to think about it, using my path integral formalism. In the path integral, I calculate the amplitude for a particle to go from point A at time t1 to point B at time t2 by summing over all possible paths connecting those points. Each path contributes a complex number, an amplitude with a phase. Now, here's the thing. Until I complete the calculation and square the amplitude to get a probability, none of those paths is the path. They all contribute. They interfere with each other. The delayed choice experiment is the same. The photon doesn't take the path through the slits. It takes all paths, and they interfere according to the measurement setup you eventually complete. Your choice of measurement determines which interference terms survive and which cancel out. So in my formalism, which I trust because it gives the right answers, there never was a single definite past to begin with. The past is a superposition, just like the future, until you anchor it with a measurement. And here's what really struck me. This means that reality is not a four-dimensional block of space-time where everything that happened is happening, and will happen already exists in some eternal present. That's the classical view, reinforced by relativity's treatment of time as a dimension. Instead, reality is more like an evolving network of correlations. Quantum events establish correlations, entanglements between systems. These correlations propagate forward in time, becoming more and more classical as they interact with larger environments. Eventually, you get a macroscopic world where the past looks fixed and determinate. But at the quantum level, where you can preserve coherence, the past remains negotiable, not changeable, but not yet fully specified until you complete the measurement. Wheeler was right, in a way, when he talked about participatory universe. We're not passive observers of a pre-existing reality. We're participants in the creation of definite outcomes. But it's not our consciousness that matters. It's our physical interactions. Every measurement we make, every experimental apparatus we set up participates in determining which aspects of quantum reality become classical, definite, and real in the historical record. And that, to me, is beautiful. Because it means the universe is not dead and fixed. It's alive with possibility, constantly crystallizing into actuality through the physical processes we call measurements. You know, I've spent my whole life trying to understand nature, how it really works, not how we wish it worked or how our intuitions tell us it should work. And quantum mechanics has been both the greatest tool and the greatest challenge in that quest. The delayed choice experiment forced me to give up something I didn't even realize I was holding on to. The idea that the past is a solid foundation, already written, unchangeable. That seems so obvious. It's embedded in our language, our thinking, our experience. But it's not how nature works at the deepest level, at the quantum level. The past is more like a musical chord where multiple notes are sounding simultaneously, and your measurement is like applying a filter that lets you hear only certain harmonics. The chord was always there, containing all those harmonics, but which ones you hear depends on the filter you use, and this changes how I think about reality itself. Reality isn't a thing, it's a process. It's the ongoing establishment of correlations, the spreading of entanglement, the decoherence of superpositions into definite outcomes. We live in a reality that's constantly becoming, not one that already is. Does this mean the future changes the past? No, not really. What it means is that time doesn't work the way we classically imagine. The past, present, and future are not separate rooms connected by one-way doors. They're more like different aspects of a single quantum process, and which aspect you see depends on which measurements you make, which questions you ask. I've made peace with this now. It took me years, but I've learned to stop imposing classical intuitions on quantum systems. I've learned to trust the mathematics, to follow where it leads, even when it challenges my everyday experience. And you know what? I find it exhilarating. Because it means nature is stranger and more wonderful than we ever imagined. It means that even something as fundamental as the past, the foundation of everything we think we know, is not what it seems. It's richer, more subtle, more quantum. When I teach students now, I tell them, don't trust your intuitions. Train new ones. Learn to think quantum mechanically, not just calculate quantum mechanically. The delayed choice experiment is a perfect example. At first, it seems to violate causality to let the future reach back and change the past. But once you understand what quantum mechanics is really saying, once you give up the classical prejudice that everything must be definite at every moment, it makes perfect sense. There's no paradox. There's no time travel. There's just the quantum world being itself weird, wonderful, and ultimately comprehensible if you're willing to let go of classical thinking. And I think that's the real lesson here. Nature doesn't care about our intuitions. She doesn't care if we find something comfortable or disturbing. She just is what she is. And our job, the job of physics, is to figure out what she's doing on her terms, not ours. So when someone asks me now, Professor Feynman, does the future change the past? I smile and say no. But the question assumes a view of time that's not quite right. The past isn't as fixed as you think, and the future isn't as open. They're woven together in a quantum tapestry that only becomes definite when we measure it. And then I watch their face go through the same confusion, resistance, and eventual wonder that I went through. Because that's the joy of physics, discovering that reality is deeper, stranger, and more beautiful than you imagined, and then sharing that discovery with others. That's why I wanted to tell you this story, not to confuse you, but to invite you into the wonder I felt and still feel when contemplating these mysteries. The universe is not a clockwork mechanism ticking away deterministically. It's a quantum kaleidoscope full of superposition and possibility, crystallizing into reality through the act of measurement, and we get to explore it. We get to ask questions, design experiments, discover the rules. We get to participate in the unfolding of reality. What a privilege. What an adventure. I hope you can see what I see when I look at these quantum puzzles, not frustration or confusion, but beauty. The beauty of a universe that's more subtle, more playful, more quantum than our classical minds ever expected. And that's the real answer to the delayed choice puzzle. Not that the future changes the past, but that reality itself is far more interesting than we ever dreamed. Thank you for coming on this journey with me. Keep questioning, keep wondering, and never ever stop trying to understand how nature really works.